In this session, we will talk about digital filters. To truly understand all the math and details of designing and using digital filters actually requires a multi-year course of study in engineering schools. But we'll learn enough to be able to use common digital filter forms, and we will end up learning about and using a very important kind of digital filter for modeling the exponentially decaying sinusoidal modes of vibration, common in so many physical systems. Let's begin our exploration of digital filters by looking at possibly the simplest one, the two-point moving average digital filter. We read this equation as y of n equals x of n plus x of n minus 1, all divided by 2. The block diagram and difference equation, as it's called, show the very same thing, that the output y is a simple average of the current input sample and the previous input sample. Since this filter averages the current sample with the last, it acts to smooth out the signal a little bit and behaves as what we call a low-pass filter, favoring lower frequencies over higher ones. In fact, the highest frequency, equal to the sample rate over 2, is blocked entirely. To test that, let's run some white noise, all frequencies equal, through this filter and see the result. This code does exactly that. First, we run 1 second of white noise, all frequencies equal, through the DAC. Then we disconnect that and run 1 second of silence. Then we build a two-point moving average filter from scratch in Chuck and run 1 second of white noise through that. Let's listen. Now let's look at the spectrum of that. First, our pure white noise. We'll see that the spectrum's completely flat. Then our second of silence, coming up. And then our second of two-point moving average filtered white noise. Importantly, note this point. Note that the response of this filter rolls off with higher frequencies, such that the gain is very, very low at half the sample rate, as we predicted. Another name for this type of filter is the 1-0 filter, because it has a gain of 0 at half sample rate. There is also a 1-0 filter built into Chuck, as shown in this code. What if instead of adding the current input to the last one, we subtracted them? Let's just change the plus sign to a minus in our code, run some noise through it, and see what happens. Here we change the sign to a minus on the delayed sample. Let's run it. Whoa, it's still a 1-0 filter, but now the 0 is at 0 frequency, as we'll see by looking at the spectrum. Same noise characteristics, but now our 0 is at 0 frequency. This is a type of filter called a high-pass filter because it cuts the gain of low frequencies and lets high ones through. Another name for this specific filter is the digital differentiator because it emphasizes parts of the signal where there's rapid changes. This filter also outputs a running computation related to the slope of the input signal if we scale it appropriately by the sampling period. Remember back when we solved our mass spring damper system and we used the current position minus the last position to approximate the velocity? Well, the digital differentiator can serve this type of function, showing us the slope of a curve. So if the input signal represented position, then the output slope would be equal to the velocity. Note that we can make a curvature or acceleration filter as well by using the current sample, the previous sample, and the sample 2 samples ago. What if we averaged more samples than just 2, say 4? The difference equation for that is y of n equals x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3, all divided by 4. Let's look at the code for this and run some noise through it, and then we can look at the spectrum. This code shows a direct path from the noise to the DAC, and then paths through 1 sample of delay, 2 samples of delay, and 3 samples of delay, all added together and scaled by 1/4. Let's run that. And let's look at the spectrum. Now we have more zeros. In fact, there are 3 zeros, but we only see 2, because the other 0 corresponding to this one is for the negative of this frequency. Yes, we can make and have negative frequencies by just changing sign to minus sign, but we can't hear any difference. Those negative frequencies and that other 0 are there because the math says it has to be. So, to compare, let's quickly do an 8-point moving average, summing the current input sample plus the last 7 and dividing it all by 8. This code does exactly that, averaging 8 samples together and dividing by 8. Let's listen to that. Note that there's even more low-pass behavior, and we now have 4 visible zeros. Here, 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 and here. In fact, the number of zeros in a filter of this type is always equal to the number of delay elements.